Welcome to this session on probability distributions. Probability is the measure of the likelihood that an event will occur. It is quantified as a number between 0 and 1, where 0 indicates the impossibility and 1 indicates the certainty. Probability theory is applied in everyday life in risk management and modeling. The insurance industry and markets use probability theory to determine pricing and make trading decisions. Governments apply probabilistic methods in environmental regulations, entitlement analysis and financial regulations. Probability theory is also used in various branches of science and engineering. Here we shall discuss some basics of probability distributions. First, we define a random variable. A random variable is a real valued function defined on the sample space of a random experiment. For example, consider the random experiment of tossing two coins. The experiment is tossing two coins. Then the sample space is S equal to HH, HT, TH and TT. This is the sample space. Now, we define a variable, say x, as the number of heads when two coins are tossed. Let x be the number of heads. Then, for the event HH, the value of x is that is HH means 2 heads, that is the value of x is 2. For this event HT, value of x is 1, here 1 h, and TH also 1 h, therefore x equal to 1. For this case TT, value of x is 0. That means, for every element of this sample space, we can find real numbers. For HH, the real number is 2. For HT or TH, the number is 1. And for TT, the number is 0. That means, we defined real numbers for all the elements of S. Therefore, this x, that is number of heads, is a random variable. X is a, here x is a random variable. Random variable x means a real valued function defined on sample space, that is x is from S to R, where S is the sample space and R is the set of real numbers. Now, there are two types of random variables, namely discrete random variable and continuous random variable. Discrete random variable and continuous random variable. A random variable which takes a finite number of values or a countably infinite set of values is known as a discrete random variable, and a random variable which takes values in an interval, that is the values are in between some limits, then such random variables are said to be continuous random variables. Now, the probability distribution. probability distribution is a function f of x which is equal to p of x equal to x, that is which assigns the probability for each outcome of a sample space. For example, if we consider the experiment of tossing two coins, the sample space is HH, HT, TH, TT. Then x, let x be a random variable. Let we define x as number of hits. Then x takes values. For this event, x is 2. For HT or TH, the value of x is 1, and for TT, value of x is 0. This x is a random variable, and probability of getting two heads means p of x equal to 2, which is 1 by 4. Probability of getting one head means HT or TH, that is p of x equal to this is equal to probability of HT plus probability of TH, that is equal to 1 by 4 plus 1 by 4, that is 2 by 4. This means p of x equal to 1 is 2 by 4. Now, probability of getting no heads means getting TT, that is equal to 1 by 4 also. No heads means the value of x is 0, that is p of x equal to 0 is 1 by 4. Thus, the probability distribution corresponding to this experiment can be expressed as f of x is equal to one by 4 for x equal to 2, 2 by 4 for x equal to 1, and again 1 by 4 for x equal to 0. This is the probability distribution. That is, probability distribution is a function f of x, that is p of x equal to that which assigns the probability for each outcome of a set of a sample space. In the discrete case, the probability distribution is termed as the probability mass function. Now, we have a theorem, that is, if f of x is a probability function, then f of x is always greater than or equal to 0 for all values of x, and summation over f of x, summation f of x over all x is equal to 1. This is an important theorem in the probability distribution. This theorem is a consequence of the axioms of probability. It can be shown that any function f of x which satisfies these conditions, these two conditions, then the function is a probability distribution or a probability function. In the discrete case, we use the term as probability mass function. In order to check a given function is a probability function or probability mass function or not, we have to check both the conditions of the stated theorem. For an example, consider the function f of x is equal to 5 minus x square all divided by 6, where x is equal to 0, 1, 2 and 3. Here f of 0 is equal to 5 by 6, which is greater than 0. F of 1 is equal to 5 minus 1 by 4 is by 6 is 4 by 6, which is also greater than 0. F of 2 is equal to 5 minus 2 square is 4 divided by 6, that is 1 by 6 is again greater than 0. F of 3 is equal to 5 minus 3 square is 9 divided by 6, that is minus 4 by 6, which is less than 0. That means, if we put x equal to 3, the corresponding function is less than 0, which violates the first condition of the above stated theorem. That is, this statement is sigma f of x equal to 1 and f of x is greater than or equal to 0 for all values of x. Here for this 3, for x equal to 3, the first condition violates. Therefore, this given function is not a probability function. In the discrete case, we termed as probability mass function. The given function is not a probability mass function, PMF. Consider another example. F of x is equal to 1 by 4 for x equal to 3, 4, 5 and 6. Here f of 3 is equal to 1 by 4, because here f of x equal to 1 by 4 is a constant function. Therefore, f of 3 equal to 1 by 4, f of 4 equal to 1 by 4, f of 5 equal to 1 by 4 and f of 6 also equal to 1 by 4. 1 by 4 is greater than 0. Therefore, f of x is greater than 0 for all values of x. First condition holds. Now, the total PMF, that means summation over all x, f of x is equal to, here f of 3 plus f of 4 plus f of 5 plus f of 6, which is equal to, all are 1 by 4, 4 times 1 by 4, that means 1. That is the second condition also satisfied. Therefore, the given function is a PMF. Now, consider this example. F of x is equal to x plus 1 divided by 25. F of x is equal to x plus 1 divided by 25 for x equal to 1, 2, 3, 4 and 5. Here f of 1 is equal to 2 by 25, which is greater than 0. F of 2 equal to 3 by 25, greater than 0. F of 3 equal to 4 by 25, which is greater than 0. F of 4 is equal to 5 by 25, greater than 0. And f of 5 is equal to 6 by 25, greater than 0. That is, f of x is greater than 0 for all values of x. First condition holds. First condition in the first condition for a probability mass function holds. Now, we have to check the second condition, that is summation f of x is equal to 2 by 25 plus 3 by 25 plus 4 by 25 plus 5 by 25 plus 6 by 25, which is equal to 2 plus 3, 5, 5 plus 4, 9, 9 plus 5 is 14, 14 plus 6 is 20, 20 divided by 5, which is not equal to 1. This is 20 divided by 25 is not equal to 1. Therefore, the second condition for a PMF is not satisfied by this function. Therefore, the given function f of x equal to x plus 1 divided by 25 for x equal to 1, 2, 3, 4 and 5 is not a PMF. Now, we have a problem. We are given a probability mass function corresponding to a discrete random variable capital X as the values of x are 1, 2, 3, 4, 5, 6 and 7. The corresponding probabilities are k, 2k, again 2k, 3k, k square, 2k square and 7k square plus k. We are given a probability mass function in a tabular form. Then the question is find the value of k. Find the value of k and evaluate probability of the random variable capital X taking value less than 3, that is p of x less than 3 and also p of x greater than 3. Now, first of all we find the value of k and then we evaluate these two probabilities. Since the given function is a probability mass function, we have summation f of x is equal to 1 over all x, that is f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6 plus f of 7 is equal to 1, which implies f of 1 is k plus f of 2 is 2k, f of 3 is 2k, f of 4 3k, f of 5 is k square, and f of 6 is 2k square and f of 7 is 7k square plus k, which is equal to 1. This implies here 7k square plus 2k square is 9k square plus 1k square is 10k square plus 2k plus 2k is 4k plus 3k means 7k plus 1k, 8k and k plus 2k is 3k, 3 plus 2 is 5, 5 plus 3 is 8, 1 means 9k plus here is equal to 1 means minus 1, minus 1 is equal to 0. On solving, we get k as, this implies k is equal to minus 1 and 1 by 10. It's a quadratic equation and we can solve for k. We will get k as minus 1 or 1 by 10. Here k is the given probability values of f of x, means the probabilities which cannot be negative, that is from the first condition f of x greater than or equal to 0 for all values of x, means k cannot be negative. Therefore, this k equal to minus 1 is not taken. We take value of k as k equal to 1 by 10. Therefore, the given function can be written as replace all k. Here 1 by 10, 2k means 2 by 10, this also 2 by 10, this is 3 by 10, here 1 by 100, here 2 by 100, 7 by 100 plus 1 by 10. Now, we can evaluate these two probabilities. First one is P of x less than 3, that is probability of x equal to x less than 3 means x equal to 1, 2, 1 or 2, that is equal to P of probability of x equal to 1 plus probability of x equal to 2, that is equal to f of 1 plus f of 2, which is equal to 1 by 10 plus 2 by 10 is equal to 3 by 10. Now, the second one is P of x greater than 3. Probability of x greater than 3 means probability of x equal to greater than 3 means 4, 5, 6 or 7, which is equal to P of x equal to 4 plus P of x equal to 5 plus P of x equal to 6 plus P of x equal to 7, that is equal to f of 4 plus f of 5 plus f of 6 plus f of 7. If we substitute these values from the table, we will get as P of x greater than 3 as 19 divided by 100. Now, we have to define mathematical expectation. Similarly, expectation of a discrete random variable x. Let x be a discrete random variable. F of x is the corresponding PMF, and let phi of x be a function on capital the random variable capital X. Then the expectation of phi of x is defined as summation phi of x into f of x over all x. That is, we multiply phi of x and f of x corresponding to the possible values of x, and then take the summation, which gives the expectation, provided this summation exists. This is the definition of expectation. Here, if we take phi of x equal to x, that is the identity function, then expectation of phi of x will become expectation of x, which is equal to summation over all x, x into f of x. This expectation is known as arithmetic mean. Arithmetic mean of the random variable capital X. Similarly, if phi of x equal to x square, then E of x square is equal to summation over all x square into f of x. The arithmetic mean of x is denoted by mu. This is denoted by mu. If we take the function phi of x as phi of x is equal to x minus mu the whole square, that is we subtract the mu means expectation of x from all the values of x and taking the squares, and this expectation of phi of x will become summation x minus mu sigma summation x minus mu whole square into f of x for all values of x. This is known as the variance of x. Variance, that is the variance of x is equal to, the notation for variance of x is sigma square x or v of x, which is the expectation of x minus mu the whole square. And the positive square root of this variance is known as, positive square root of variance of x is known as standard deviation. Standard deviation. These are some basic definitions using the expectation. Consider an example. That is, in a business, a man earns a profit of rupees 3,000 with the probability .6, and he loses 2,000 rupees with the probability 0.3, and also he neither earn a profit nor a loss, is with the probability 0.1, then his expected profit in the business is given by the expectation of x, where x can be taken as the profit. We take x as the profit, then the values of x are 3,000, 2,000 and 0. Neither a profit nor a loss means we take the value of x as 0. Here 2,000 rupees loss means in terms of profit we can write this as minus 2,000. Therefore, if we take x as the profit, then the values of x are negative 2,000, 0 and 3,000. These are the possible values of x, and corresponding probabilities f of x as 0.3. Probability for 3,000 rupees profit is 0.6, and neither a loss neither a profit nor a loss means the corresponding probabilities here 0.1. This is the probability mass function corresponding to this problem, and now we have to calculate the expected profit, means E of x, as summation x into f of x, that is equal to first term is minus 2000 into 0.3 plus 0 into 0.1 plus 3000 into 0.6. Here we used the definition of expectation. This is equal to, on simplification, 3 into 2 is 6, minus 600 plus this is 0 into 0.1 means 0 plus 18 1800, that is equal to 1200 rupees. 1200 is the expected profit in his business. Note that here all the values of f of x are greater than 0, and if we add these probabilities, 0.3 plus 0.1 is 0.4 and plus 0.6 is equal to 1. Both the conditions for a PMF are satisfied. Therefore, we can use these definitions. This is a probability function, and we can use the definition of expectation. Let me conclude this session. In this session, we discussed some basic concepts of probability distributions. Thank you for watching this session. Have a nice day.